Howdy 216ers, this is Professor Kaufman, and what ensues is a video overview of your first major programming project. You've been working on various things in labs and accruing some C skills, and it's high time to put those to use in a somewhat larger context. This first project will hit all major aspects of the C language that we'll contend with over the course of the semester, and so makes for a nice culmination that you'll complete hopefully right before exam 1 hits and make use of those techniques to prove that you mastered them on the exam itself. A few notes. This project page summarizes what's to go into the project, and you'll want to refer back to it often. Probably, at least if you haven't been asleep during labs, you know the first few steps will probably involve grabbing this zip file and downloading it to wherever you work on your code, most often Grace and so forth. I want to make a mention of a couple things. Projects are a little bit different than labs and homeworks. Those labs and homeworks are collaborative, whereas this is meant to be individual work. That's not to say that you can't discuss it with your colleagues, but largely the code that you write for this should be the product of your own understanding. And if you find your eyes lingering upon your neighbor's code for too long, probably you should avert them, as that'll avoid the unpleasantness of getting detected for too high of a similarity later on. The project also has a couple different grading aspects to it, and we'll touch on these as we move ahead, but it's roughly going to be divided to half credits for manual inspection. Someone will actually look at your code and assign some style credit, but also make sure you're adhering to the guidelines and stipulations of the assignment. And then the other half will be the automated testing. There are no hidden tests, no withheld tests, no secret criteria, no bait and switch, gotcha, because I wrote a test case after release just to make people mad. What we deliver is exactly what will be evaluated on for credit. So as you run automated tests, we'll look at how that works in a second, then you'll see results, and those should be reflected when you eventually upload this to GradeScope. So you'll know at least part of what your grade will be after you on submission there. Okay, let's get into it a little bit. As before, in the labs, for instance, there's a manifest that indicates what files will be delivered. Mainly, you'll be editing the bandlet funcs and bandlet main files. For the first couple problems, these utility functions, and then later on for the last problem, completing their use in a main function that involves a few things like command line on Power BI. Those are the older files around. For instance, there's a header that's provided that will indicate the data types that are at stake, and those are worthy of study, as well as a few demo files. One that shows some syntax associated with parts of what bandlet looks like, as well as a file that demonstrates command line handling. This is going to be useful as you'll want to lift techniques from there and use them in bandlet main.c. There's one final C file that's provided. It's called bandlet font standard. It looks a little bit weird because it's essentially a big data file that encodes a built-in font to what's there. And we'll get to that business later on. There are various other things around, for instance, testing files, some data files, some stuff that's used specifically for testing and so forth. Generally, you don't have to look at those too much, except that when you should start running tests and find that you have bugs and so are failing tests, you may want to poke around in this test results directory, as that's where the results of tests will be stored, and they reveal a lot of information about how to go about debugging and improving the program to pass those tests. As with the labs, there is a make file provided, and so the standard sets of commands are there. The verbiage is maybe just a little bit different. For instance, if you wanted to build everything, create the whole program, it's just a plain make, or build only the code that's associated with problem 1, the sort of utility functions, that's a make prob 1. Most likely, you'll all be testing, sort of running and testing things. So a make test prob 2 to run the automated test associated with problem 2 is probably fine. If you don't want to wait around for all of the tests on problem 2 to run, that instead you're focusing your attention wisely on a single test, then you might add on the test num equals something and keep grinding away on that one until you pass it there. A few other things in here, notably when you want to submit, there's a make zip as well, and that will create a p1 complete.zip that you'd upload, and we'll maybe touch on that a little bit later. If you've not been asleep in labs again, then you're probably aware of all this stuff, except that running the automated tests in this case for the project will produce a lot more output because there are a lot more tests. It's a bigger project to sort of go through. But as they were for some of the labs, the tests will be named, and then as you would fail things, there'll be a file mentioned over here where you can look at the results. Running single tests like that will print them immediately to the screen. And before submitting, you'd probably want to run this make test, which will run tests associated with all three of the problems. Okay, the content of the project itself is to construct a little program called bandlet. It's invoked with bandlet main here, and the central idea is you provide a little bit of text here, and it prints it as a banner. This is sort of in the tradition of old school Unix or internets where there wasn't much by way of fonts and so forth. So people constructed their own sorts of fonts in the terminal. That the character H is represented by this glyph here. Glyph is a fancy word for a little picture to draw so that humans understand it. But you could vary that and say, I actually draw this little picture here by using a separate font. So you can immediately see from this, there are a couple of things at stake. Taking the raw ASCII characters that are here and converting it to a sort of picture-like entity here, that'll be partly interesting. And as well, then, you can vary how each of the characters are drawn by feeding options to the executable as a font file. The final variant down here says, let's take the text from this file, data asimov.txt, one of my favorite authors, and instead of having to type out the entire thing on the command line, I can just load it from there, and as well use a different font file, yet this little mini font that's a bit more compact. Not compact enough to fit in without some scrolling, but there it is over here. I do not fear computers, I fear the lack of them. Probably an appropriate quote for a computing class like this. So at the outset, this is a fairly primitive purpose, but it's going to take us through the regime of many things that we've seen in terms of C stuff. Primarily, your first couple problems here are going to deal with this bandlet funcs.c file. And a manifest or list or sort of outline of what's in that file is present in the project specification here. Each of the functions that's required is followed by some documentation here, but since we're nice instructors, we're going to provide for you a skeleton of this file already. And in fact, it compiles out of the gates, has the necessary functions in it, and the documentation associated with it that's in the comments there. Annotated along with the functions is the problem that they correspond to, and well, this is a bit nebulous. Mainly these break down to, the automated tests are going to test this set of functions, string replace char, count line breaks, find line breaks, etc. And then later on down here, there's stuff associated with problem 2. For instance, loading a font from a file and so forth. So the last problem 3 that's down here, deals with the main function. There's also a compilable skeleton provided for that, and we'll maybe touch on that just a little bit. Your main cycle is going to be as follows. Once you get the code downloaded and updated and unzipped, you'll probably start looking at it, making some changes codes, and then running make test prob 1. That will, in all likelihood, cause all failures at the moment, but getting the code compiling is the first step towards victory. So that means you can run tests and sort of start to look for correctness. If you were to look, for instance, in this first file over here, this test results prob101 results.txt, there'll probably be something that looks kind of like this that shows a test results and the reasons that there was a failure associated with it. For instance, down here, there's a failure listed as there's an output mismatch at the lines marked. This section in the middle shows a side-by-side difference. There's an expected output for the test and then an actual output that your program produced. And you can see there's a little symbol in the middle here, a little bit obscure, but this shows there's a difference between the two lines here. That the expected result for this thing on printing here is that all of the A's were replaced by X's. So rather than AABBA, you get an XXBBX. And we'll have a look at how to fix that up right quick in a second. That's because the intent of the test here, and this is the testing code that's actually run, is to call your string replace cars function and replace all instances of A with the letter X. we'll see that the initial state of things is like, well, you get almost exactly this result because this function is empty. It doesn't do anything. And so it won't alter the string that's at stake and produce erroneous results. We can fix that up right quick in a lot of cases. So looking at this can produce a lot of informative guidance about what's going wrong and how you might go about fixing it, including that down sort of below the side-by-side diff is the results of algorithm runs, which will indicate whether or not you had memory problems. And sometimes your output matches exactly. It's just that there's a memory problem. You went out of bounds, tried to use something in an uninitialized fashion. That isn't the case here. However, it can come to pass. And so you'd want to look towards the top to see what is the summary of why I'm failing. So in this case, it was just an output mismatch, but there might be messages here as well about memory errors there. Okay, so let's get into a little bit. We'll start with a discussion of this sort of these string utility functions. What you'll notice is that there is throughout the sort of outline of the project specification here, there's various sections that deal with how to implement different functions, including somewhat detailed guidance about things like looking for null characters using Sterling, how to identify new lines, and so forth. And so I'm not going to go through all of these in the video overview, but we will attempt to solve this string replace car function first, just to get sort of oriented. And then we'll round back around and start looking ahead at what's to come in problem 2 and problem 3 there. Okay, for that effort, I'm going to switch over to a code editor. I'm running right now in my local Linux environment. I run Linux natively as I find it more convenient for work. However, you'd want to make use of whatever environment you've been coding labs in. For instance, if you're logging into Grace and making use of that, then by all means do it there. And in all likelihood, if that were the case, you'd probably zip back up to the top here, copy this link here, copy the link address, and then do a wget on that in order to download it to whatever machine you're on. Make use of MOBA Xterm or Xquartz or VS Code, whatever you find most convenient to work in here. The point is, on right-hand side, I've got terminal, left-hand side, I've got a little file browser, and at this stage, I should be able to unzip that p1code.zip. And if I refresh over here, you'll see I got a p1 code directory, change in there, code here, and do a listing. Left-hand side, which shows the directory. I've got the stuff that was listed in the manifest, and then over here, the little ls indicates the same bit of business there. So the first thing you might try to do is what we talked about, is a make test. I'm going to restrict this to problem 1, as I don't want to run all of the tests, just the ones pertaining to the problem that I'm focused on right now. As usual, this will compile the code and then start showing me test results. I'll make this window just a little bit bigger so you can see. Not doing so hot in terms of the functionality yet, but then that's sort of expected on account of I haven't written any code yet. And so as we'd want to work on this string replace car function, which is the first series of tests here, I'm going to find it in code and fire it up. To do so, I'm going to come over here to the bandlet funcs file, which has all those. And you can see in here in source code, there's that documentation string associated with what this function is generally supposed to do, as well as an assertion that you're supposed to write me. So I find in many cases that if you can locate examples of what a function is supposed to do, of input-output behavior, this is an expedient way to come to grips with what exactly it's supposed to do, and then you can maybe look at further verbiage about specifics about what it's supposed to do. So here's an example of that given. So there's this string 1, which is AABBA. Should be familiar because it's actually one of the test cases there. And as I had called the string replace car function, pass in this string S1, I should get the additional arguments are replace A's with X's. And this should alter the string in place S1 so that it now reads XXBBX. Importantly, this doesn't allocate a new memory. It will work on the memory that's provided in here, so altering it. And so whatever this function is doing, it will affect the world by changing A's to X's. Similarly, I could change B's to Y's. So this is a second string, S2, starts out the same way, but alters all the B's to Y's. So here I had B's, but now they're Y's there. In this last invocation, alters whitespace, this little space character here, and plops a dash down, so all the spaces that were between those A's and B's, they're dashes now. Again, a separate string, so I'm not modifying the earlier one there. Now, a few things that you should sort of sort out or mentally come to grips with here is like, okay, I have a query character, I need to look for it somehow in the string, and then plop something down in its place. There are a few bits of advice given in the doc string as well in the project specification that we'll look at. For instance, you might iterate through this string using a loop. You need to know how big it is. Sterling is good for that. Alternatively, as you iterate, you might detect the end of the string by looking for a null termination character, this little \0 there. So we can futz a little bit and try both of those things in code as we like. If you wanted further detail and guidance, the section again was the string utility functions here. And so there's some more advice about this, including some syntax that is there to remind you of things like, oh, you can assign things to arrays, including strings, which are just character arrays, by using square brace syntax. And then the literal syntax for characters involves this little single quote character. So plopping down a single quote A here would assign to the ith position of the array the capital A there. Just keep in mind what we've talked about in lectures, that strings themselves don't carry a length. They're either a plain array or a pointer to some array of characters. They don't have a length field, they don't have a length function, there's no length method, and the size of stir won't work inside of your function string replace char. So you need to use one of those other two alternative methods to find the end of it. As well then, as you're searching, if you're looking for a specific character, the equality check will also be handy. Don't make use of the assignment operator, which is this single thing there. Now, with all those things in mind, let's go ahead and just, take a crack at this thing. So as a first pass, let's just do something dumb, which is let's affect the string. Let's change it in some way. So I've got this stir here as such. I'm going to assign the 0th element of it to be my favorite letter in the alphabet, a K. And all I'm looking for here is to see, will this affect my test results? So I'm going to open up a terminal on the right-hand side here. Let's see, get my shell back there. And I'll use the handy syntax I had before to run the tests, except since I'm just trying to pass this first test here, I'm only going to run that one. So I'll write test num equal to 1. So that'll do two things. It'll run the test and plop results down over here. Oh, we should actually look at those results quick so you can see what they look like here. So if I open up my little file browser and refresh, you see, oh, there's a new file in here called test results. You open that one up, and then there's results files for each of the tests that were run. That'll always be the case that all tests get a results file, even if they pass. I find that's easier for my consistency, but I have heard students say they'd like to be able to just limit this to the number of just failed tests, and I'll consider offering options for that later on in the class. But if I open this thing up, it'll probably look a bit fancier than it will on yours. Probably yours will look more like this, sort of plain text in that respect. But hey, what can I say? Emacs is an amazing editor, and so I'll learn about it at some point if you're so inclined. But what we see over here is more or less what's expected in terms of test failure results. A big fail at the top, the failure message, sort of as was described to expect in the specification, that there's an output difference that's problematic. And that output difference is mentioned down here. Don't have anything in terms of problems for Valgrind, and this line differences thing is just a reiteration. Sometimes it's hard to see when it's side by side exactly what the differences are. This sort of top to bottom thing makes that a little bit easier to see in that respect. So should be X's, instead it's by A's, the expect versus actual. Now, I'm going to, let's see, just make sure I save that file here, this band. Let's see. My editor will be like, if I make a change, it puts a little star here. So I'll do that. It looks like it's saved. So first thing in it should be a K now. I'll need to rerun, but I'm going to just rerun that first test. And in this case, since I only ran one test, you can see the test results printed right on the terminal here. if I flip back over to that thing here and it refreshes, like, yeah, indeed, I see that as well here, so there's a K. So when working on a single test, it's handy then to be able to just run that test and you see it immediately in the terminal. You might have to scroll a little bit, but no matter there. And you see, yeah, my code actually was affecting by this, because what was an A is now a K. What I really want is X's in that respect. So, you know, a Goomba programmer might say like, oh, let me like put an X here because, you know, that's what the test case wants. So, of course, all of you know at this stage, yeah, that's going to change the output, but it's not really what you want. You need to visit the entirety of the string and plop things down. So here's a semi-Goomba approach. You need to iterate through the string. So give myself an int I equals 0, because that's where the thing. Fill this in just a second, and then I++. And we'll do something like stir I equals X. Now here's where I need to figure out what's my loop bounds, like how far through the string should I iterate. If you weren't asleep for the earlier part of the discussion, you recall, oh, there's a strlen function that will tell you how long a strlen, the string is. So here's I less than strlen of stir, that. And the header file that's included up here, I believe, includes the string.h, so I don't need to do that here. Let us just check that quick. So here's bandla.h, also a good one to look in. And yeah, when you include this one, it includes the string.h file as well. And so no need to include that elsewhere. Later on, we may have you start including some of these things yourself, but for the first project, it makes sense to include one header and away you go there. If you like, you can start looking through this thing. We may touch on it just a little bit later, but some of the data structures that pertain to bandlet's printing actually are at stake there. But these first few string functions are easier, and so won't matter too much. Okay, so I made my change here. I'm going to change the ith element to X as I'm iterating all the way over the entire string. We'll be good there. Minor note here, repeatedly calling strlen is maybe not the best way to do this, but later on in the class we'll talk about better alternatives of that. If you like, I may as well do this non-Goomba move here, is move this outside and call it once, as I don't expect the string length to change. Still Goomba-esque, but no matter there. Okay, so that's change. I can just invoke make test prob1. The beautiful part about makefiles, and we'll look at this later on in the class, is that it will detect that, the source file, the .c file, is a little bit different. So I'll automatically recompile all the stuff that I need to run the test properly, and then run the test based on the updated code. Super handy, and you'll see the little GCCs up there. You see I've made some progress in that I've at least affected the whole string, but hey, X's are not exactly what we're looking for. I mean, there are some in there, but not the spaces or the B's and so forth. So now we have to get ever so slightly more sophisticated. Probably unconditionally changing everything in the string to an X is not so good. So instead, maybe I check like if, let's see, stir I, a specific character is the character A, then I will change it to an X. Seems reasonable because the test case up here is that if it's an A, change it to an X, and we're good to go there. Most of you are probably groaning at this point. It's like, oh, come on, Kaufman, we're not, that dumb here. But, oh my God, I passed the test case. Hooray, huzzah! We're good to go. Like, so then at this point, like, oh, let's see if I pass all of them. You could limit a little bit, but of course, if you're groaning, like hard-coded against a test case. That's not really the general purpose functionality we're looking for. Quick tip, if you press Control-C while these are running, you can stop them from running. This will bail you out of the testing. You can see a little testing thing is like out of signal, and I'm going to bail out right now. So it saves you the trouble of like waiting to get your terminal back there. So let's bop around and see in the test results what's wrong with number 2 over here. So that was test results down here. Have a look at number 2. It's a fail over here. And the side-by-side difference, let's see. And that's because I was supposed to, in this case, be changing B's to Y's. And instead was changing still A's to X's. So, Goomba programming at its best there. So let's then correct for that, and this will be a giveaway of the first function, which most of you probably already finished, like while I'm blathering here. But really what I should be looking for is not fixed strings here, fixed characters rather, but I'm looking to see, I want to replace an old character with a new character. So this is replace if the thing that's in the string is the old character, assign it to be the new character. And you're good to go. For you C++ers or Javers, new is not a keyword in C, so we can make use of that. Zip back over here, rerun those first few test problems, and we should have a general expectation of good success for the string replace. And we're more or less at that point on to count line breaks and its ilk. So if that didn't impress you terribly, then that's fine. These first few functions are intentionally somewhat easier. Find line breaks makes these starts to get a little bit interesting because you actually have to allocate some memory. And print fontified will probably take a little bit of time for all of you because it's an interesting algorithm. I want to spend a little time on that, so we're going to fast forward past the string utility functions and instead talk about this section on print fontified here. So the essence of what this program is eventually supposed to do is to print a series of glyphs. So if you were printing just the character A, it would print as something like this with the default font that's there. Well, this is broken down into several steps. The first one is to have a one-line function that you print one line that in its entirety, like sort of one line of text in entirety in this fontified fashion. Now, even this proves to be a little bit onerous because unlike a standard sort of display like this, you can't just paint a pixel at an arbitrary spot. Text displays, terminals, they move from left to right and then to the next line. It's very reminiscent of old video game systems on CRTs where there was an electron beam that scanned across, and so you had to sort of paint things according to that ordering. So if I wanted to print something like cat here, you're reduced to doing the following sort of algorithm that is demonstrated here, but is one that then you'll have to sort of code up. The letters I want eventually are down here of cat, but I can't just print the C first and then move to the A because moving left to right here, I'm going to have to hit all the top parts of the A's and the T's and so forth. So generally that looks like, and we'll use this little @ sign to represent the position of the terminal cursor, is print a space followed by some underscores here, which constitutes the top parts of the C. And then print some spaces here and a little underscore that constitutes the top part of the A. Leaves the cursor here. And then print some underscores, which constitutes the top part of the T. Then we print a new line to carry down to the next line with the cursor here, and proceed to print the next row of characters that correspond to C. So that's this little /, a space, and then some underscores, and a little pipe or bar here. And now I've got another row of what the C character constitutes. And then a couple of forward and backward slashes, and then some pipes and underscores for more of the T and so forth. And then a new line, and we can sort of continue to fast forward. It's like, I'll print another row of the A's and T's, print another row of the C's and T's, and then finally print the bottom part down here to complete this. So to do this effectively, then, you'll need to access the data that is associated with these glyphs. The picture that's associated with A, the picture that's associated with C, the picture that's associated with T, otherwise referred to as glyphs in font terminology. Now, if you have any experience with fonts, like working in a Microsoft Word doc or a Google Writer doc or stuff like that, you can like highlight stuff and then go to some font menu and pick all manner of like wonky looking stuff, and it changes the shapes. The underlying data is that there's something that says paint a T here, paint a C here. And we'll be restricting our situation to the ASCII codes. And so this will essentially be a number between 0 and 127 that says which in the alphabet should be displayed there. Not all ASCII characters are letters. Some of them are like ats and slashes and so forth. And generally speaking, then the glyph in our little text-based font is going to be some collection of those to paint here when you are supposed to place a C down. Now this brings to mind then the data structures that we saw in the header file before. Glyph itself here as defined in a glyph T, is essentially a little 2D table that has some limits, maximum height, maximum width, of characters, so cars there. So in this case, like, some of the characters were underscores, some of the characters were backslashes, some were forwards, some were pipes. We'll actually see letters and tildes in some fonts and so forth. So that's the essence of what goes in here. The code point here is associated with the number in some enumeration of different glyphs that could be displayed. ASCII runs from 0 to 127, and we'll talk about this more later when we get to the representation of various things in binary. But for instance, as an example, ASCII code 65 at that code point is a capital A. If you're curious, you can go look around, and we'll talk a little bit about the history of like why is ASCII 0 to 127, and how would I draw other things like non-Latin characters from other parts of the world. Unicode expands this to much bigger than 127. But this is complex enough as it is. So each of these pictures to be represented, like the A up here, then is represented in one of these, encoded in the program as one of these little glyph T structs here. And a font is just then an array of these. The array here of glyphs then is one that contains an entry at 0 and 1 and 2 and 3. And ironically then, like, at entry 65 in that array, that's where the picture associated with capital A will be placed. Now, it might be worthwhile at this point to jump over to one of the data file that's provided. In the the code pack, there's a font standard.c that lays this out. And here at the top of this is a bunch of pictures, glyph standard 128, shows 128 because we're hitting all ASCII characters. And what's in here is a bunch of gobbledygook to begin with, but then eventually you get a little bit further down and see, the data part here, it actually has a picture. This one's supposed to be an equal sign, this one's supposed to be in a semicolon, and as we get down to 65, here is the capital A, and the capital B, and the capital C, and so forth. We'll look in a second at the font files, but they have a sort of similar character to this. I should mention as well, some of the ASCII characters were not going to be supported by the fonts that are provided, and they'll have a rendering that looks sort of like this, that this 0 code point is actually the null character, and it's non-printing, so we don't have anything to draw here. And I forget what code point 1 is in the ASCII table, but you can look at it, or it's some other non-printing character. Go a little further down in this, maybe way further down, you get to some numbers, and then beneath that, at higher ASCII codes, are the lowercase characters. And while they don't look particularly lowercase, this one actually doesn't occupy the top line. It's like a sort of small caps A and so forth. No, sorry, I'm still looking at caps. I'm confused. No, I think these are the lowercase. Yeah, so anyway. But then there's other things as well, like, here's a square brace and so forth. So, and in that respect, then, this array then is encapsulated at the end of this source file in the glyphs for the standard font, which has a maximum height of 6, so none of these are bigger than 6 rows big, but they do have some variance in terms of their width. So some are 5, some are 3, some are 1, some are 8, etc. So that's the essence of what the two data structures are for this particular project. One is a glyph T that works on this, and the other is this font T type that is essentially a glorified array of glyphs. Now, the astute observer is going to look at this header file as we saw it and say, well, hold on a second, Kaufman. If glyphs is a pointer to an array of stuff, and it is there, how am I supposed to tell how many elements are in this array? Because you've been hounding us over and over in lecture that arrays and pointers in C, they don't carry a length associated with them. And to that, I had to respond, we have a special situation here. The ASCII code that we're trying to come up with glyphs for, it only runs 0 to 127, so 128 total. So you can assume that this array is 128 long in each case. And that's why we don't need to carry a length with it as you would for another arbitrary sized array. To that end, then you could exploit that, and we will in the project to deal with things. For instance, initializing a font, you just initialize this thing to a raw 128 long array of stuff. That won't always be the case, that not every array is 128 long, it turns out, but we can exploit that special structure in this case to avoid needing to carry a length around. That said, not every font is going to support every character, so there is a font in there that doesn't have any of the lowercase letters, and a bunch of the fonts don't have like some of the weird non-ASCII character or non-printing characters, like carriage return and new line and that kind of stuff. That should hopefully assuage doubts about where's the length for this array. We don't need it because it's assumed to be number of ASCII glyphs, 128 up here. These little bits, pound defines up here, essentially lay out substitution so that when the compiler looks at this thing, the max height will be substituted for 10, the max width will be substituted for 20. Not the most flexible design, but hey, this makes this thing a lot easier here. And we'll talk hopefully about pound defines a little bit more later on in the lecture, as they're useful for some contexts like this and oft used in C programs. Here, don't need to worry about that too much, but for the moment, you may want to make a note that this num ASCII glyphs here is useful. Okay, so this whole business started as we were sort of trying to talk about how do you actually go about doing this algorithm. Well, it's useful to look at a bit of C code that's provided, this bandlet C demo, or bandlet demo.c file, as it reveals some syntax that's useful for accessing glyphs and so forth. So I'm going to pull that up in my code editor because I don't like the way that this is highlighted here, and I'll have to look at why it's got this ugly green thing going on, whereas the other ones had much nicer looking stuff. But that's here, the bandlet demo.c. So you're going to have to access several things here. For instance, as you load fonts, like this font standard one here, oftentimes in code as you're working in the function that you eventually have to write, have a pointer to a font like that. And as you're marching along in some bits of code, you might find I see that I need this integer code point, like this A here. Now notice I've assigned this character A to an integer over here. And that's because under the hood, this is just a sequence of bits that says paint A here. If it's painted in a character context, then it will print out an A. But if it's painted as an integer, as is assigned here, it'll print out the number 65, or at least the decimal number 65. There are other ways to write it than that. Now, that should sort of start to trigger this dual representation of they're all bits, so you can interpret them as something other than a number or just as a number, as we're doing here. And with characters represented or equally equivalent as numbers, that means you can do things like, print it here as a number, %d here. Or alternatively, use it as an index into an array. So for instance, here's this A, it's ASCII code 65, and I can reach into a glyphs array that's 127 long, grab out that 65th element and do some things with it. So the glyph itself, it needs to go through the font, so that's a bit of indirection here. So there's a pointer, so a pointer to a struct that needs to be dereferenced, so thus the arrow. And we'll talk in lecture more about dots versus arrows. Dots associated with plain structs, arrows associated with pointers to structs here. And since we've made font up here a pointer to a font T, we'll need to do that dereference. It has a glyphs part, and I should probably pull up over on the right-hand side that header file so we can chase this. It has a glyphs part here, which is a pointer to an array. So if I plop down square braces here, that's another dereference. It gets me to one element of that array, which is a glyph T. Well, the glyph itself has a bunch of parts. It has a code point, it has a width, and as well it has this data part here. And so the next part over here demonstrates some syntax associated with it's a 2D table. If I index it once, that gets me a whole row of stuff. It's a row of characters, so you can print it out as though it were a string. So my intent here is not to belabor this, but you'll likely, as you get to the print fontified function, want to review that information as it's presented in the project spec here, and also look at some of the demonstration codes out there. Perhaps reading this as well to see this would be a row of characters, this would be a single character, etc. Those things will be useful to you to come to grips with it. As well as then sort of looking through and chasing this algorithm to sort of get a sense of this is how I'm going to print things. Is that you're repeatedly going to scan across the string out there. Now, with that done, the next step will be to move to the next problem. And that just expands the print one line of stuff to here's a multi-line string, print that in a fontified fashion. That's not going to be too bad. It's going to be repeated calls with a little bit of like pointer arithmetic indexing into the string. It'll be in good shape. The next major step that a lot of students stumble on is to deal then with the aspect of where you want multiple fonts. So there's this standard built-in font that's part of the executable and the C library that's provided. But ideally, you want to be able to offer some variants. And so, as is commonly done with normal fonts that you display in web browsers or Word docs or whatever, we'll have some files that encode the information needed for a font. Now, you can poke around these font files. They're sort of interesting to look at. They're in the data directory and all prefaced with a font underscore prefix there. So for instance, this alternate font, if you looked at the beginning of it, you'd see at the top there's a height 6 because all of the glyphs in it are 6. And then there's a series of numbers in here. So essentially, each glyph that's actually encoded in the font file starts with what glyph number is it, number 32, and then has some drawing associated with it. If you're looking and not blind, and apologies to those of you who are looking this blind, it makes it a lot harder to understand this stuff. There's a bunch of question marks here. The question marks are meant to ease the input processing, and we'll talk about them a little bit more later. But if you poke around a little bit, you'll see things that sort of look like a question mark, and this one's sort of like a hash, and so forth. So the structures will be more apparent in a second. Get down to ASCII code 65, which is some distance into that font text file, and you'll see something that kind of looks like an A, a B, a C, and so forth. So feel free to poke around those font files. Each of them is a little bit different. Now, the question marks are there because we could plop down white space here, but it turns out C processing of text files is actually quite hard when you have to deal with white space. So the question marks are here to say, all I really need to do to read lines of this glyph is to use an fscanf and a %s to read in some stuff. Read that into one part of a glyph, and the part you'd probably leave into is one row of this data over here, and then read the next line into the next row, and then to the next row, and so forth. And the number of rows you'd read would probably be something like the max height associated with the font. And then, after you've read it in, call that handy-dandy string replace character functions you wrote before to get rid of all the question marks, which should instead be spaces here. And so this ASCII code 65 with the question marks in it will be converted to this much nicer looking rendering that has spaces, and you can clearly see the ABC at this point. So there's additional information in here about that stuff, as well as a few advisements about some provided functions that when you would load a font in this font load function, you'd want to start out by allocating memory for the fonts and each of the glyphs, and then initializing them so you can obviously detect the initialization function that's provided will plop down this thing in there so that you know if you missed something there or end up printing out a character that isn't in the font or something like that. So analyze that stuff somewhat carefully. The final function for problem 2 is to slurp a text file. I learned about this one, I think, in grad school. Slurping is essentially just take the entire contents of some data file, be it text or binary or something like that, and copy it into memory someplace. Now, there are a bunch of different ways to do this, but there's going to be a prescribed way, this baseline method, that you all should implement first. And then if you're feeling sassy, you can try to do the optional makeup credit version of this, which does this in a single pass of I/O. There are a bunch of restrictions on this stuff, and so if you want full credit on the baseline, do what's listed here, and do as well what's listed in the docs for this thing. So if I scan down to that in the bandlet funcs.c, let me find, let's see, say slurp. Yeah, down here, there's a bunch of restrictions about you must do it in this way, you cannot do this kind of thing. We'll talk about alternative, potentially more efficient ways to read an entire file later in the class. But the prescribed method is 2 passes through it. The first pass, you read things but discard them just to count characters that are in a text file. This can be done either with an fscanf or an fgetc, some advice on that in the project spec. Then you rewind the file, and there's a handy rewind function in C that allows you to take some file handle and zip back to the beginning. Once you count all the characters in there, you know how much to malloc, so you can malloc that amount, and then on the second pass through the file, read them into the space that you operated on. The optional makeup credit part here does this in a single I/O pass, so read through it once, but I'll let you diagnose here the restrictions on this. This is essentially to educate you if you've never seen an expandable or dynamic array before. Use the techniques that are associated with that. Then read some into a smallish array, and when you run out of space, allocate a new bigger array, usually twice as big, copy what you have, or free the old array, and then proceed forwards to read more. In this case, it's a bit tricky because you have to deal with the I/O simultaneously with the array growth there. But it's an excellent programming exercise, and if you abide by all of the restrictions here, then you can earn 10 points of makeup credits. Not extra credit, but makeup credit in case you screw something up on this project or the next few that are around. Goes into your project pool in that respect. I won't say more about that other than to say that unless you have a baseline version, TAs won't help you with this version. And so it's probably a better idea, finish the whole project in normal mode and then go back and do this slightly hard mode thing here. Now, why is this slurp file a thing? Well, it's to support an option later on in Bandlet itself, which is to support reading stuff in from a text file. So this is where if someone said Bandlet with this text file here, so they have a long sort of diatribe they want to print it in banner form, so they have to put it on the command line, slurp that file in, and that becomes the message to print out in that way. So the last problem is to construct a main, and that main function is provided as a skeleton over here, bandlet main.c. There's a bunch of provided parts, including some suggested variable names. But then, as there are in the functions, there's a bunch of required parts that you'll need to fill in here. Oops, I'm giving away something here that you're supposed to use call print fontified. I'm going to delete that from there because it's not supposed to be there. But none of you were going to get fooled by that anyway. So the main thing that's difficult about this is the command line processing, which will maybe be a little bit new to some of you. And it should introduce you to this idea that programs that are flexible on the command line, they can be run with a variety of different options in different orders. If you've been tracking with our lecture discussion of GCC, it has gobs and gobs of options associated with it and can accept things in lots of different orders to make the life of programmers a little bit easier. Bandlet's a little bit more modest. You can pass a string to be printed. You can pass a string to be printed along with the font to use, but you can vary the order of font specified first here and then the message. Or you can say grab it out of a text file, grab out a text file and use this font file, or use this font file and grab this thing out of this text file. So essentially all variations of these. Someplace there has to be a message either coming from a raw string on front or out of a text file here. And then optionally you do the font file business. This can be super intimidating at first, and a lot of Goomba programmers will come at this and say, well, there's 6 cases here, so I guess, Bob, I'm going to have 6 if-elses and somehow detect each of these and have each of them. And at the point that I add a new option, like dash interactive or something like that, they're like, well, Bob, I've got now 12 different cases for this because I could add a dash interactive in a variety of different spots over here. In fact, it's probably more than 12. It's more than that. So I've got a lot of cases now, Bob. After a little bit of a consideration, you'll recognize some structure here that's actually these options is like semi-independent. For instance, the font file says load a font up. Text file says this is your message, or this is your message is coming on the command line string. And so a better option is just to iterate through this thing. To say, how do I get at command line arguments? Let me iterate through them. If you've not dealt with command line arguments before, or have never seen anything like that, C provides them as the arguments to main. And this is a very interesting sort of approach. Different programming environments do this in different ways, but this is super traditional, and it's the same in Java. So Java main will have not 2 things here, but like a string args, I think, array, something like that. So C is a little more traditional, like all arrays, you need to carry a link with you. So argc is how many command arguments there are. And this carstar argv, it's an array of strings or array of character pointers to be dealt with. There's a handy little demonstration file for this that is, oh shoot, I forgot. I should have put it in the code pack, but this is why I oftentimes do these videos first, is I forgot to put it in there. So let me grab it out quick. It actually comes from lecture too, so let me grab, what's the fastest one? Probably the one that's in the project, because I can find that quickly. Go to the solution, and it's this command line args.c. Yeah, so I'll make sure this is in the code back so you have access to it. This thing shows output that is contingent on what's in the command line for stuff. So if you just compiled it, command line args.c, and ran it, then there would be this little, there's one command line argument, and it is a.out. If you put four things, more things on there, like you ran a.out with apple, banana, and peach, then the 0th argument would be a.out. That's the name of the executable that's running. It's in the 0th spot on this command line array here. The 1th thing is apple, the 2nd thing is banana, the 3rd thing is peach. So that should give you some sense of like what the intent is here. I've added a little pizzazz to this thing, and I want to see, so come over here to do some stuff. So let me GCC this command line args.c. You can see to print things out, it has a little loop here, and all it does is like, I loop up to argc. I will print out the ith thing, and the ith thing is going to be coming out of this argv array, which is just an array of strings, so I'll print them as such, as strings here. So let me run that quick. There's a.out, and I'll put apple, banana, peach, as we had before, as you can see that over here. The bit of pizzazz that I added, aside from spelling banana wrong, is to add one special thing that's looked for, the option. And so there's a special check here done to say that if what I'm looking at is the fixed string, the option, and bear in mind this use of strcomp says if there are 0 differences between this thing and this string, then execute this code. In that case, some special action is taken. And so if I run this again with the option at stake, then you'll see in addition to printing it out, there's a special message, and afterwards we get the hooray, the option was set. Now that should inspire you a little bit about how you might seek to handle the options in bandlet here with these -- font files and -- text files and so forth. And if it doesn't inspire you, I've got yet further inspiration down here, a bit of pseudocode that's in a Python-esque dialect. I mean, it's nothing special. Syntax idling is pretty terrible, but no matter, I'm sure you can parse it, which sort of outlines the approach that you might want to take, including little nuggets like, if you have a -- font file that's on there, then you should grab the next thing, which will be the font file to load. Load it, and so long as it worked, then move ahead, because you've actually used up both font file and this next thing here. So update your loop variable so you move to the next thing there. Now this structure is much slicker because as sort of expandability of code goes, is like, any new options like -- interactive just becomes another case in this if-else over here. There are some minor conflicts, like for instance, what happens if I set my message to be displayed in banner text using -- text file, and also do so with a sort of plain command line argument here? You don't have to deal with those. These are the only valid ways to invoke bandlet, and your program can fall, crash and burn, print errors, messages of your taste, if someone invokes it not like this, and we won't be testing you that stuff, so don't sweat it if you do something funny or arbitrary out there. Okay, so once you finish up the main, then you're free to sort of experiment a little and print out some messages. And if you're particularly artistically inclined, then you might go find and add some new font files and see if they work with this thing. I actually adapted some of the font files hosted on Figlet here to be used for this project. Figlet is more complex because it deals with some actual like font stuff, which is interesting. Stuff like kerning, where you mash characters together a little bit closer than they would be in the rendering, that we won't do. So that can make it a little bit harder to adapt the fonts that are present there in this. But there's a lot of them, so maybe you find one that is sort of fun to make use of. And I guess looking at the dates for when these fonts were published, it starts to date me just a little bit, but no matter. Classic Unix program, that. All right. Aside then from all that business, all that remains when you finish the thing up is to run all the tests, make a zip, and then upload it to Gradescope, just as you've been doing for labs. Make sure to check that your Gradescope results reflect what you have locally. More than one student has submitted at 11:50 p.m. On the night of the deadline, called it quits, and then found the next day that there was something wrong with their submission. Like, oh my God, I uploaded the distribution file that has no code in it, so I failed all the tests, and I'm supposed to be passing all of them. That is on you. Make sure to check. It usually only takes 2-3 minutes for the Gradescope autograder to run, that you get what you expect over here for this. You ignore some of the specifics in these pictures because they deal with an older project at a different university, but the gist of it should be clear here. Final word of advice, we will accept late projects, but it'll cost you 1 engagement point per day. So up to 2 days late, 1 engagement point on the first day, 2 on the next day. Keep in mind that engagement points are like, oh, I finished this lab, I earned an engagement point. But I now lose that lab if I'm submitting a day late. The lecture participation, piazza participation, discussion participation, those aren't direct engagement points. So if you raised your hand and answered a question, that might be 1 engagement point, but it's probably less than that because those things are judged on a logarithmic scale. So your first question and answer, that's 1 engagement point, but you need 2 more to get another engagement point, and then 4 more, and then 8 more, etc. So be careful about that. I have had students who submit every project 2 days late and say, well, I raised my hand 10 times in class, so that's going to cost me, but it will, unfortunately, it will. All right, that's all I got for you. Expect office hours to start ramping up in terms of busyness somewhat as folks start to work on this project and find the difficulties associated with it. But this is part of doing CS stuff, is writing some, I wouldn't say real programs, but more complex programs and coming to grips with the complexities of doing so. I need to update my email address on this, but aside from that, this thing should be in pretty good shape. I'll see you all in lecture. Happy hacking until then.